I will try to put up the assignment. Assignment 4 today. Maybe at night I will try to upload it as well as with the solutions for assignment 3 as well. So I will try to do that tonight or early tomorrow morning. I will try my best to give it to you. Otherwise, I don't have anything to say. Also, the context. Okay. So I was hoping to finish most of the Heap part today, and if we have a time, then we can go into some of the applications of the Heap or leftist tree, things like Huffman tree or scheduling algorithms. Hopefully we can get that far today, or as it is okay now. So we've been discussed last class and class before that, little bit on the class before that. We were discussing on the basically a tree and different type of trees and mostly binary trees, right? Last class I wanted to emphasize on the complete trees, right? And then if you mixing up all those definitions, then max tree, min tree, what was a max tree again? Definition of max tree, or how are they look like? Max tree? Well, what was one obvious property of a max tree? So one on the top is probably the largest in the tree, right? The value is the largest. And the minimum tree is probably the opposite. So we also cover how to number a node in a tree, how to read the tree. Last class we also looked at how to implement for that level order reading ways, right? What data structure did we use to implement that? What data structure was in use? Level order. Q, right? Because it's simple push and pop. Not push and pop. They use the push and pop, but I would say DQ and NQ operations. So you wanted to print out the node from top to bottom, left to right. As they encounter, you will visit them. Visit means print out the values of each node. 그죠? And then we start discussing the max and min tree. Now you're gonna divide it into max binary tree, min binary tree. And if you start putting the term max complete binary tree, then they have a different name for it too, right? What was the name for that part? It's right here though. Complete. Min or max tree that is also a complete binary tree is something called Heap, right? I already give you some hint on where we can use this Heap type of stuff. Later slide I have it. If we can do it nicely, then maybe we can use it to sort a numbers or any type of sorting that we like to do. So it also depends on max and min, so you can do a descending or ascending order of a sorting. That might be one obvious applications of this Heap. So we just discussed the definition of a Heap. We didn't take a look at how they actually look like, the addition process, deletion process, and how to even create a Heap at the first place. When we're discussing those type of operations, what is a natural way, what is the next thing that we usually discuss after how to create those stuff? Well, 맨날 얘기하는 거지. After we discuss the data structure, we look at the very basics of the class definitions of our textbook or slide, and then we usually move into different set of operations, and some operations might be a bit difficult to implement. So, and then we discussed that we usually go into time complexity, right? So it's a bit strict tree. So hopefully we have a good time complexity for addition, deletion, as well as the making Heap at the first place as well. So again, definition of a heap is max or min heap, max or min tree that is complete binary tree. 이건 뭐 다 할 거고. So don't get mixed up. Max tree or min tree doesn't necessarily to be a binary tree. Just in general definition of max tree, you can have a multiple edges, multiple node as your children. So that's one thing, just to do not mix it up. I was just wondering, what is a complete tree then? Just to remind you. Complete tree. Can you see the tree and can you tell whether it's a complete or incomplete tree? What is a complete tree? How do you define a complete tree? 어떻게 complete tree? If you have n node, if you're gonna number them 1 to n, if you miss a number in the between, it may not be complete tree. If you draw on the board, then if you're missing a left side of node, then it will be not going to be a complete tree. We will see the examples. This first one, is it a complete tree? This one. Is it a complete tree? How do I tell that? I usually do this. I just number myself 1, 2, 3, 4, 5, 6. Okay. I don't have any numbers empty between. The second one, is it a complete tree? Oh? Is it? 1, 2, 3, 4. Okay, no. Incomplete tree, 그죠? 이거, is it a complete tree or incomplete tree? 1, 2, okay. So that's one of the easy way. I'm not sure that's an exact definition. That's how I usually find out. The definition that we wrote in our slide, they usually also say so 1 to n, if you miss an element, then it's not a complete tree. So incomplete tree. Again, do not mix it up with the full tree, full binary tree. Is this full binary tree? No. Is this full binary tree? No. No. When we had a tree like this, what was the term to describe this type of tree? Example that we had was this side. What was the name they usually call in our textbook? Tree on the one line. That was discussed when we were discussing the space waste of space in installing implementing tree on top of arrays. 뭐라고 그랬어? What was the name for this? Yeah, I think they call a right skew tree, but this one is on the left side, so we should call it a left skew tree. So, the issue was there's too much gap. If it's a right skew tree, there's too much gap because numbers go 1, 3, and then it goes like 7, quite large. So a lot of gap in the between. So you should know. Because eventually I will ask you to generate your own heap. One of the common mistakes is you don't even have a complete tree. You're missing a node in somewhere. Then it's not a heap, okay? So it's another first thing to recognize is whether you know how to read a complete tree. And you will have to write it in your own hands. Very, very common questions that I can ask you in exam situations. I give you set up numbers and create a heap tree. It's another way of saying maximum complete binary tree, max complete binary tree. Okay, well, it looks quite easy, but I guarantee you, if you don't do it at least once, then you will probably mix it up. 이것도 마찬가지로 손으로 안 써보면 눈으로 보면 되게 쉬운데 손으로 안 써보면 그 헷갈리는 것 중에 100% 하나예요. I still do. Sometimes I forgot how to create a heap myself. So you need some very tiny bit of practice, then you'll be fine. So this seems to be a max heap and 9 node. Complete binary tree with a 9 node that is also max tree. Let me see whether it satisfies the conditions for max. Okay, it seems the parents always bigger than 뭐지? Children. Okay, 9 is on the top, 8, 7 is smaller. on this type of tree, also on the left side of tree, A6, 6, 5, 1, okay. 2, 6, it is also seems to be a complete tree too. So it's a max heap with a 9 node. Mean tree, exact opposite, the smallest one on the top. And when your children will be greater than yourself, than roots. So that's another way of saying it. So like I told you last time, what if I start taking the elements off from the top? Take 2 out. What's your next step then? If I take 2 out, so I wrote it somewhere 2. Now I have 8 elements. What's your next step? Yeah, maybe you want to reorganize. Another way of saying is you're also making another heap. So every single time you might need to, you're changing your trees to make it heap. So I'm going to call it as you're also making another heap tree. Likewise, you're repeating that process. Take 1, heap tree. Take 1, heap tree. And so it says a heap is efficiently representing as an array. The heap can be, there's 2 ways. Implementing we are discussing priority queues, right? This is all about priority queues. The 2 ways to implement the priority queue was, the first thing they suggest is heap, which can be implemented on top of arrays. What was the other one? Which we haven't looked at it yet, but it had said so in the first set of slides. What was the name for the second one? 뭐냐? Leftist tree, they also said it can be implemented on top of using a linked list chain, right? 2 ways. Just don't get confused. We're still in the priority queue discussions, right? A heap is efficiently representing an array because it's a complete tree, so I don't have any waste of space in the between. It will be much easier later on, even if what does it mean I take out 9 from this array? Maybe I just take out the first position. Yeah, it's quite easy to take 1 out. I know always, if I take out 9, I'm doing a heap again, then probably another first position will be the biggest one in this tree as well. So it's quite easy to just take the first one out. Take the first one out. And there's no waste space in between the elements, so it's a nice way of doing so. So that's a heap in array representation. Obviously, you can see the a good thing about it. When heap operation, when n is the number of elements, so I'm dealing with the n elements in the tree. How long does it take to insert an element? It doesn't really matter whether it's a heap or not. We're dealing with the binary tree, max binary tree or mean binary tree. Doesn't really matter it's complete or not. Complete, nice. Obviously, what might be the insertion cost? I'd like to add a new node into a tree, including finding my position in the tree. Because if you don't know what are you dealing with, but as soon as you heard the word binary, your wild guess should be log. Because I'm assuming that I try to go from top, I have some elements on the try to add. I ask myself to ask root, is this bigger than me? If it's bigger, then I should replace. If it's smaller, I would try to find a way down there where my position should be, right? Then you are asking questions hand half and half every time you make a decision left to right, left to right. So eventually you can assume something called log. It's quite obvious. Deletion as well. As soon as you delete one, well, regardless of the heap, if you want to delete something, you have to find it first. What was the finding cost in a binary tree? Obviously log n. 매번 들어갈 때마다 반반씩 쪼개지니까 log 2 of n. Initialization, we'll cover it, but it's a bit obvious. You are making a new heap. In the worst case, you have to look it through every single element to find the position. If you think it that way, it's quite easy. It's quite easy. Of course, there are formal definitions, formal way of calculating how we obtain n, but I usually don't think of it that way. Just look at the big picture and do a wild guess. No one's going to ask you how to come up with this. Well, in some case, they do, but that's how I do it. That's how I usually think of it. I think that's more important. I mean, understanding what it is. 약간 꼼수라고 봐도 돼요. 근데 큰 그림을 보고 생각하면 이해를 하면 훨씬 편하잖아. 그죠? So let's take a look why they take a log 2 of n or order n for initialization. So I like to insert something into the max heap. In this case, the red one is the new element. I like to add 5. I like to add 5. So in the array of thinking, maybe in that array that I have, I like to add a new element at the end of the array, maybe. Okay. Is this good? Is this good? 7, 5, I just added in. Okay. 5 is less than 7, which means if I'm less than 7, on the top, it's naturally assumed that everything will be bigger than 7. So I think I'm not breaking any rules about heap. So I think I'm done. The simple addition is just done. What about 20? I like to add 20 maybe at the end of array. What should I do next? Yeah, I should compare myself to my new parents, which has a 7 in it. 7. So it's my max heap. So if I'm bigger than my parents, I should switch the place between my parents. So 20 should go up. 20 should go up. Okay. I'm in my new position now. 7 is below me. Okay. What else? What can I do next? I'm also comparing again, right, for the next level. My parents, now my new parents is 8, 20. So I need to switch again. Switch again. It makes sense, right? So you're doing a recursive way of doing it. 20. Okay, I'm in now my new position, 20, and my new parents, which is also root, is 9. 20, compare 9, obvious. Another switching operation, 20. I'm on the top. Are we finished? Probably it will be now at the front of the array. Front of the array. It's jumping around the array. 계속 array로 하면 이렇게 그려놓으면 20 was here, jumping, like this. So, switching places. Are we done? Yes, I think we're done. Everything is now under definition of a max heap. So, obviously, we just going back one up. But how many times did we do that? It's probably about the height of the entire tree. How do you determine the height of the tree if you have an n node? How do you determine the height of the tree, or the other way around? If you have h height, what's the total number of a node in the tree, in the binary? Or 2 to the h minus 1, which is also 이거 n 노드면 하이트 어떻게 돼? 로그 n 하면 하이트 나오지, 그죠? So obviously that this insertion process, it's a big O of log of 2 of n. 그죠? It makes sense. 매번 한 단계 올라가는 단계가 총 키잖아. 키라고 그래야 되나? 트리의 키잖아. 그죠? 트리의 키는 log of n이니까. 물론 이제 full tree에서 그렇게 하지만 큰 바운더리로 log of n이니까. So it's obviously, as we've seen from those examples, it's quite obvious that each level we do a constant work. Each level we do a constant work, which means we do a comparison and switch. Switch, just take a one operation, one. If we need to switch, just one operation, or do a comparison at the same time. Everything is one constant operations. Thus, the time complexity is order of a height. For that example, we do a 4 switch. 그죠? 아래서부터 4 switch. That is also same as log of big of log n. 말 되지? Where n is the heap size. 물론 이거보다 좀 크겠죠. n이 이건 full binary tree는 아니니까, 그죠? 근데 큰 바운더리는 저게 맞으니까. Will it be so different from a deletion operation? Deletion도 비슷하겠지, right? If I delete something, the bottom one should be switching around to find the next element in that spot. That is also will be doing a order of a height operation. 내가 혹시나 해서 물어보는데 잘 이해가 안 간다. 이해 가지? 그렇지. 그럼 가겠지. So it's pretty much same process for the deletion part as well. Max element in the root. What happens when we delete an element? So I like to delete the root, which is the maximum value, which is 20 out. After max element is removed, what can you do? What are you doing after this? I need to find a replacement. Yeah. So in terms of replacing replacing the new elements, I do it like I'm gonna reinsert 8, which was already there. I'm gonna reinsert 8 into a heap from the top. Reinsert from 8 goes on the top. Take out the last element. I'm gonna put that in the root position where it was. It's one of the ways. Reinsert 8 into a heap. We finished. So max heap doesn't seem to be right. 그죠? What else? What can I do after this point? You can see is, 15 is bigger than I am. I just do a comparison. I just do a switch. 15 on the top now. Cool. And 15 and 8 switch the place. At the same time, I'm also comparing to the one and below my level. 8, 9, 6. 9 is obviously bigger than 8. I switch. 8, 7, okay. 7 is smaller than 8. Do I need to switch? No, I stop. Are we finished? Yes. This one, we didn't go onto the bottom layer, but in big O definition, in the worst case, you can go down entire levels, right? So it's just, so it's pretty much same thing as insertion complexity. Quite obvious. Oh. 지금은 둘 중에 아무거나 가도 됩니다. 네. 나중에 이 다음 챕터에 나오는 거는 왼쪽은 작고 오른쪽은 크고 그런 룰이 또 하나 들어가는 트리가 또 따로 있어요. 바이너리 서치 트리 같은 거는 또 바뀌어요. 지금은 둘 중에 아무데나 가도 돼요. 네. 맞아요. 왜 안 물어보나 했습니다. 당연히 물어볼 수 있는 거라고 생각하고요. 둘이 같아도 둘 중에 아무거나 선택해도 상관없습니다. 지금은 둘이 같아도. 아니요, 그냥 처음 보는 거 해도 되고, 나중에 나오는 거 해도 되고 상관없어요. For more details, if you can take a look at some of the, I'm not so sure in the textbook provide the deletion code. If you take a look at the implementation for these operations, they probably do. They do consider both cases. Just pick one, or first one they encounter, just switch. Doesn't really matter. It's a similar example for 12.4 in the textbook. Deletion examples. Time complexity of deletion is obviously same as the insertion part. At each level, we do one constant work. You just do a simply comparison and switch. Switch is 뭐야? 그냥 how do you do a switch in array? You just position switch. It's constant. 그냥 인덱스만 해갖고 서로 바꿔주기만 하면 되니까. So thus, the time complexity is order of height, which is equal to big O of log of n, where n is the heap size, total number of elements in it. 다 했네. You're done heap. There's nothing to do more. After this is just repeat of, it's giving another example of the heap, and just make sure you know how to create a heap. That's probably it. Heap initialization, max heap initialization. Heap initialization means to construct a heap by adjusting the tree if necessary. For example, I give you input array like this. So if I draw that, how do I draw that? Let's say 1, 2, 3, 4. 맞나? 5, 6, 7. 그죠? That's a position of a tree in this way. Of course, this is empty. This is not minus. This is empty because we kind of ignore the 0 positions, right? We discussed that. Huh? 몇 번 얘기했잖아요. If you wanted to know the element number of a left side was 2i, if it's I, 2i plus 1 이랬잖아. If you start from 0, it's a bit complicated. 0, 0, 0, 1. So just one of the cautions. But some other implementations, they do actually start from 0. So our textbook just try to make it simpler. Just waste one space. It's not gonna cost much. 이러면 계산하기 좀 편하니까 그런 것 같아요. 별로 마음에 드는 것 같진 않은데. Otherwise, you have to put a lot of error checking points. 귀찮으니까. So like this. 1, 2, 3, 4, 5, 6, 11. That's an input array. So how do you make this heap how do you make this as a heap? Start max heap initialization, making heap tree from initial random tree. Start at the rightmost array position that has a child. So try to look for the rightmost elements, which is not a leaf, but it has a child. Okay, so that gives me 5. 가장 오른쪽에 있으면서 그 child를 가지고 있는 거. 6는 가장 오른쪽에 있긴 하지만 they have no child. 그렇죠? So definitely start at the rightmost array position that has a child. That gets me 5. So from that point, I do the same thing, comparing, going back up. 5. 미안. Sorry. 5 and 11. So I compare. 11 is bigger than 5. 10이 올라오면은 11보단 작으니까, 그죠? So maybe you wanna, when you're implementing it, you wanna compare which one is the biggest and then switch back to. After that, you do the same thing. Next rightmost node that has a child, which gives me 4. See? Next rightmost node that has a child, which is 4. Do that. So 8 and 9. What else? 9 should be up and running. 그죠? 9 should be up. And then the next, so is the left side, rightmost node that has a child in it, which gives me 3. So 6 and 7. So 7 should be up, switching the place. Next one will be on that 2. 맞지? 7 and 3, 2, Now when you try to compare 2 and 11, so 11 is up, 11, 2 switch. 1 is up, which was the root from the beginning. I'd like to find out the 11 and 1, 7 and 1, so 11 should be up. So I'm switching place. And then you do that for that part. So 1 will be down there. 1 will be 계속 1 내려왔으니까 1하고 또 그 아래 있는 애들하고 비교해서 1 should be moving down right side like that. Are we finished? Are we finished? Done. So you just did a hippie. Some people call it hippifies, but I'm not so sure that's the right term. But you just made a hip initialization, hip initialization. After you giving a very basic tree, you did a hip. Done. Done. Next step, what is the time complexity of this hip, making a hip? I already told you it will be order of n, because in worst case you need to go through every node, do the comparing and switching, right? This was one of the nicer cases. That was a brief analogy. To be exact, this is how you actually calculate it. It's okay. It's not my concern. So see figure 12.5 for another initializing examples. Please do try with your hands. And then goes like height of the hip is still h. Number of node at each level is j. Each level j. So number of node in each level j. 하나의 j. 이렇게 보면 level 1, level 2, level 3, 1, 2, 3. Say number of node in here is probably 2 to the j 뭐야? 맞나? 2 to the j. What is it? 2. Number of node in this. Number of node in this level is 2 to the 3 minus 1, 4. Makes sense, right? This way. And that's for the time for each node at level j. The number of nodes at level j. The time for each node at level j is this. This is how much time they take. Time for all nodes. So you're adding this all up. Each level, how many comparisons can you do a max? You have to go up, go down. Then you add them all, you will have something called order of n. Don't worry about it too much for the last 2 lines, but you will get the idea. I mean, like I say, it's basically say you have to go through every single node if in worst case. You have to do the comparison to finding its right place. After this, it's just practice. 나 이거 그리기 싫은데. Do exercise for 12.7. 이 다음에 그려놨구나. 12.7. 10, 2, 7, 6, 9, 6, 5, 9, 12, 35, 22, 15, 1, 3, 4. I think one of the assignment questions will ask you this anyways. So I'm going to skip it. And the previous example, also another example on your textbook is probably good enough. 이거 뭐 자꾸 얘기해봐야 유치원생 하는 거니까. So, but I know that a lot of people will not do this for practice. You will have to do this. You will have to do this. 내가 in my experience last term, when I ask you to draw a hip tree, I get all kind of tree, which is not complete, which is not lined up, which has no numbers or mixed up. Some part of the tree is max, some part of the tree is mean. 눈으로 보면 금방 쉽게 할 것 같은데 작년에 비슷한 문제를 냈을 때 상당히 매기기 힘든 경우가 나왔어요. 한 절반 정도는 힙인지 틀인지도 모르게 그려놓은 사람들도 상당히 많았어. 한 번씩만 그려보면 절대 안 잊어버리니까 해봐요. 특히 아까 전에 인서션이나 딜리션 같은 거 새로운 게 아래로 들어가서 위로 들어오고 뭐 위에 거 없어졌을 때 제일 맨 끝에 있던 걸 다시 위로 올려줘서 다시 해서 내려오고 하는 것들 꼭 그런 거 봐요. 그죠? If you look back at those stuff, So it seems every deletion or insertion, I'm doing a heap again, right? So what's the total complexity? What is the total time complexity of doing both of them at the same time? I might need to do a heap. Making a heap is taking order n. Taking a deletion is order log of n. Maybe I need to time those two. N log n, probably the time that I'm doing the entire operation, making heap again, right? Right? 그지? n 하나 뽑아오고 넣는데 log n 걸린다 그랬지. 뒤에 나오긴 하는데 log n 걸린다 그랬지. Okay. It's taking out means it's not n yet. Whatever left over I need to do. 아이고. So I can do this again later. I need to make it a heap. So in fact, they actually need probably. This is probably time course. 좀 이따 나와요. sort 할 때.
근데 힙 만드는 데는 n만 들고 그 다음에 로그 n만 들고.
근데 그렇지. 근데 이제 다시 힙솔트 하는 게 또 꺼내와야 되잖아. 그러면 힙을 만들어 놓은 상태에서 또 꺼내야 되니까 힙은 어차피 또 만들어야 되니까 꺼내고 나면 힙이 아닐 수가 있잖아. 다시 힙을 맞는지 확인을 해야 되잖아. 아까처럼.
그러면 마지막 노드만 제일 위로 올리고 한번 정렬하면 로그 n만.
그러니까 worst case는 n. 힙을 만드는 worst case는 n이니까. worst case는 n이니까. 케이스로 얘기하는 거예요. 뭐 실제로는 n밖에 안 걸릴 수 있어도 worst case n이니까. 이거 조금 이따 나와요. Anyway, why am I saying this? Because what is the general time complexity that we know about in sorting algorithms? Not this course, probably outside the course. I usually say n square. Any sorting algorithms, probably worst case bound is n square. What was the midterm question on 뭐였지? I want you to line up the time complexity. It was order n, 아니다, log n, n log n, 뭐였니? n square, 2 of n, 3 of n, n factor, 뭐였나? 맞나? Maybe. And then it was like, and. Wow. Okay. So obviously this one is log times log n is smaller than n square. But it can also do a sorting too, right? So it's much better. This, if we use a heap to do a sorting, it might be much better than any other sorting algorithm that we know about in terms of time complexity. 그치? 일반적으로 sorting 알고리즘은 n 스퀘어로 알고 있었잖아. 근데 이렇게 하면 얼핏 보니까 지금 로그 n도 될 것 같으네. 좀 나을 수도 있겠죠. 그죠? This slide will come up later anyways. This heap 10, 2, 7. This is the one we have 10, 2, 7, 6, 5, 9, 12, 35, 22, 15, 1. Making heap. 뭐 어떻게 되는 거야? 12, 7, 12 and 7 switch. 바뀌어 계속 올라가는 거 보여주는 거예요. 35. The bigger numbers keep going up. This one, C, after 15 is inserted, 15 is up on the top. Keep switching. I mean, it's quite obvious. You can take a look at it later. Skip it. 이렇게 보니까 너무 헷갈린다. Okay, please do follow these examples if you have time. 뭐 앞에 예제랑 똑같으니까 it's not so much different from my previous examples. Leftist tree. We know from beginning it's a chain. It's a linked list, not array anymore. So let's take a look at what it is. Despite the heap structure being both space and time efficient, it's good for space and time efficient. Time, log n. Space is probably the n. It's nice. It is not suitable for all application of the priority queue. Like in the beginning, when it's usually linked list is a good way to represent a tree, right? So why not use a tree? Leftist tree structure are useful for applications like to meld, combine a pairs of a priority queues using multiple queues in varying size. Sometimes you may need more than one queue with a different size. Then if you wanted to combine those stuff, then leftist tree is good example for that. We didn't take a look at any multiple queue examples yet. The closest one that we have discussed, probably the supermarket one. If you wanted to have a cashier, have a different capacity for the customers to serve, then it's those cases are right. Or again, the more stuff will be coming in operating systems. In the computer program, when they try to schedule a different programs, they actually have multiple priority queues. Each queue have a different purpose. And then you select the one from those queues. Sometimes you move around the queues. Sometimes my elements in Q1, next time in Q2. Those things are also possible. If so, it's better to use a leftist tree, the linked list one, than array ones. Leftist tree is a linked data structure suitable for implementing a priority queue. The tree which tends to lean to the left. lean이 뭐야? 기울기 이렇게 쓱 lean to the left. 자꾸 add하고 하다 보면 자꾸 왼쪽으로만 자꾸 달리게 되는, 이렇게 뭐 많이 하게 되면 자꾸 그쪽으로 자꾸 가게 되는. 레프트 스큐, 라이트 스큐는 진짜 다 이렇게 되는 애들이고, 이것도 이제 오래 러닝을 하다 보면 그렇게 될 수 있는데 이제 막 그 정도까지는 아니고. Tends to leans to the left. 뭐 레프티스트 트리 여기 지금 우리는 크게 커버는 안 하거든요. 근데 우리 어레이로 힙 만들다 보면 그냥 어레이는 계속 그 안에서 빙빙 돌잖아. 링크 리스트니까 뭐 예를 들어 계속 엘리먼트를 달아주고 막 이렇게 하잖아. 그래서 나중에 트리를 그리다 보면 많이 레프티스트 트리를 써서 이 구조를 써서 힙을 막 구현하고 하다 보면 자꾸 이렇게 트리가 이렇게 컴플리트 트리가 이쪽에 더 엘리먼트가 더 많아 보이게 되는 거예요. 이쪽은 최소한만 되고 이쪽에 자꾸 더 달려 보이게. 이쪽에 자꾸 왼쪽으로 기운다요. 이렇게 그런 형태로 가게 되는 구조가 되더라라는 거예요. 됐어. 라이스 큐는 완전 이거고. 프라이어티 큐. 그러니까 지금 하는 거를 링크 리스트로 구현을 하니까 되는데 이거 잊어버려. 이거 하나의 프로퍼티가 그렇게 링크 리스트를 자꾸 달다 보니까 왼쪽으로 자꾸 달리게 되더라라는 뜻이에요. 그거는 책에도 잘 안 나와. 그냥 하나의 현상일 뿐이에요. 현상. 뭐 좋다 나쁘다는 뜻으로 얘기하는 게 아니에요. 하나의 현상으로 한다는 거예요. 우리 레프티스트 트리는 커버 안 해요. 커버 안 하고 그 하나 예제로 뒤에 나오는 예제로 보여줄 거예요. 허프만 코드나 이런 거를 보여줄 거예요. 그냥 어렵게 생각하지 말고 내가 제일 처음에 그린 거 있지? 이렇게 이거 구현하는 게 레프티스트 트리라고 보면 돼요. 그리고 책에 보면 또 이렇게 나오기도 하는데 여기 보면 멀티플 큐라고 돼 있잖아. 큐 사이즈가 다른 거. 이 큐는 뭐 한 3개 정도밖에 못 가질 수 있는 거. 여기 4개밖에 못 가질 수 있어요. 그래서 큐 안에도 큐끼리도 또 프라이어티가 있어갖고 하는 게 있는데 이거는 오퍼레이팅 시스템에 조금 더 나와요. 여기 나오는 요 데피니션 정도만 알고 있어요. So we mostly discuss on the heaping. Heap is more important. Heap array-based representation is the one. So application of heap, I already give you a hint on sorting. Heap sort. This is called heap sort. Heap sort. Without even looking at that, what might be the time complexity of this heap sort? We do have a basic understanding of a heap. So probably time complexity of heap sort is n log n. And next problem is machine scheduling. Machine scheduling. It's some problem that doesn't have a solution in it. Machine scheduling. You have many jobs to finish. You have, for example, in the computers, you have many programs running. You have only one CPU. Your program's waiting for CPU to do something for you, right? And what order should I serve my CPU so I can finish all the program in best time? Like that. Huffman codes, I will give you. 내가 Huffman code 올렸나? Did I upload the Huffman code? Okay. Those are the one small slide that I found on the nets. It's a good example for the explaining the benefits of the Huffman code, more of a compression algorithms. Ah, yeah, you guys cover some of the compression algorithms in Introduction to Computer Science. 할 때 하지 않았어? 허프만 코드 좀 나오지 않았니? 허프만 코드는 안 나왔니? 근데 그 Introduction to Computer Science 할 때 첫 번째 과목 할 때 컴프레션 비슷한 거 나왔지. 이렇게 뭐 많이 나오는 글자 이렇게 갖고 거기서 허프만 코드 안 나왔었나? 안 나왔었나? 잊어버렸다. Anyway, let's take a look what it is. Heap sort. Use an element key as a priority. Algorithms. Put elements to be sorted into priority queue. Initialize the heap. That's what it means. You have many elements ready, many numbers ready. You're going to put that into a heap, make it into a heap, and then next step is extract or delete the element from the priority queue. Delete the element from the top of the heap. If it's a max, mean or max, doesn't really matter. If it's a mean priority queue, elements are extracted in non-decreasing order of a priority. 0, 1, 2, 3, 4, 5. If it's a max, elements are extracted in non-decreasing order, not increasing order. The biggest one first. Biggest one first. Okay. 뭐 뻔하지 뭐. This is the example for that. This is a max priority queue. So in this big circle, they will make a heap. They will make a heap and delete, yeah. Extract one by one. 저 안에서 이제 힙 만드는 거예요. 힙 만드는 거. 힙 만들면 probably the bottom one, this is max. Okay. 야, 이거 맥스가 아니지 않니? 아, 맞구나. 맥스 맞구나. I'm sorry. So it's max. He's taking out the largest one first. I thought it was a mean. Take out the largest one first. You put that in the last position in the array. Likewise, 6. As you take it out in order, put that into sorted array. So this is not the array for the stored in the heap. 이거는 힙 만드는 그 어레이가 아니라 그냥 나오는 결과값 넣는 다른 어레이예요. 혹시 헷갈리지 마요. So you can have a sorted array at the end. Good. That opens a new possibility. It's no longer n square. Probably the log n, n log n is the smallest the lowest time complexity that you can have in sorting algorithms at this moment. So C program 12.8 and 12.9. When you take a look at 12.8, it also gives you the little bit of information, the implementation details on constructing the heap and taking the elements out. Usually have a comparison statement, comparison and switch statement. Heap sort also 12.9 for your own exercise. So heap sort n elements. initializing operation is order of n times. Each deletion operation takes log of n. Thus, total time takes is order n log n. Why? Because the heap has to be reinitialized after each deletion operation. That's, I mean, after we take one out, we have to reorganize it so we can call it heap again. 그치? 하나 빼놨으니까 나머지 거 뭐 이렇게 아래에 있는 거 적당한 거 갖다 올려야 되잖아요. That's the same process, the heap, making heap. But we know the worst time complexity of making heap is order n. So we're just gonna compute that as n log n. 성원이도 맞아. You're right too. I mean, in most cases, once we have a nice heap, take one out, probably just take a, but maybe in good cases, order of a height. 내려가기만 하면 되니까. But we're discussing in worst time complexity. So we're just going to assume that making heap is order of n times. N log n, that's what it means. So compare with the order of n square for sorting methods in previous chapters. 뭐였었지? What was the sorting method that we discussed? Insertion sort? 뭐 이런 것도 있었지? 또 뭐 있었지? I forgot. Selection sort. We didn't discuss it too much for the algorithm itself, right? But we know that in order to sort an element, in worst case, I need to compare one element to every other element in the list. I mean, that was the basic understanding of the sorting algorithms, right? So I usually tell you those are order n square algorithms. You guys taking other courses for the sorting algorithms and stuff? 그치? 다른 과목에서 sorting 알고리즘에 대해서 구체적으로 컴퓨터 알고리즘 다음 학기 하는구나. I'm sorry. Maybe 쿠츠너 교수님 거 하지 않니? 2학년 때 아니? 미안. 거기서 할 거야. 여기서 sorting 알고리즘까지 하면 귀찮아요. 머리 빠져. So, but you guys know how to read it. You guys, hopefully after this course, you guys don't know how to actually write it, but you guys have a rough ideas how they actually look like in terms of big O's. And not as much as omega, but big O probably gives you idea for that part. And log n square. Machine scheduling problem. You have m identical machines. Another application for priority, possible application for using a priority queue. Maybe you can use a heap too. So it's a problem for like this. There's m identical machines. There's m machines. 어이쿠. Okay, machine M1, M2, M3, M4, I don't care. And so some type of machines can do something, and there are n jobs. So there are 어떻게 그려야 돼? n jobs, n1, n2, n3. I can give n1 job, this job to m1, so it will do something and it will tell me when to finish. Likewise, like this. And each n1 and n2, n2. This one will give me, it will take 10 seconds to finish this job. It will take another 5 seconds to finish this job. And 3, I don't know, 20 seconds to finish the job. It's all the same machine. So my goal is, if I have maybe 10 jobs with a different lengths, and I have 4 machines, how can I give, how do I find out which job to give to which machine? So overall waiting time would be the smallest. 내가 머신이 예를 들어 할 수 있는 기계가 4개가 있고 내가 한 10개 일을 해야 되는데 각 일이 전부 다 필요한 시간이 다 틀려요. 하고 싶은 거는 이거를 이렇게 잘 분배를 해서 모든 일이 제일 최단시간에 끝내게 하고 싶은 거예요. That's the problem that they try to attack. But good news, bad news? One bad news is there is no solution for this. There is no formula to solve this problem. How do we do this in human brain? We can schedule ourselves, right? 보고, this is short job, so I'm gonna give to this or the shortest job to one machine. I'm gonna assign a longest job to another machine so they can finish roughly the same time. Those type of thinking is possible for us, but in the mathematical formulas, there is no best solution to find out the scheduling. So the machine scheduling problem is to assign a job to machines so the time at which the last job complete is the minimum. 되게 작은 거. So this is the case like this. 3 machines, 7 jobs. Job times is first one takes 6 seconds, 2 seconds, 3 seconds, 5 seconds, and 10 seconds, 7 and 14 seconds. What are some possible schedules? So all the same machine. Maybe if I do this, I give 6 seconds, and then I'm gonna give a 7-second job in here. So A will end in 13 seconds. Likewise, B will give in a 2-second job, ending at 7, 5-second job. And then 7, 이거 빼면 얼마냐? 14 job, 14-second job. Likewise, so overall time, when does this all the machines will end? 이렇게 하면 21 second, at the 21 second, everything will be done. Can you find a better scheduling for this? Okay. The better scheduling. 나는 머리가 안 좋아서 못 찾겠다. 맞습니다. 예. 나 OS 들었구나. OS에서 나오는 거 똑같은 거예요. 맞아요. 거기서 어떻게 했지? 거기서 막 하는 것도 있었죠. 아무거나 막 가져와서 막 하는 경우도 있었고. 그죠? So we're not discussing in operating system purpose. That's in the implementation details. If you want to take a look at it as a mathematical problem, then I'm just looking at that. So if we have that, if we sort it, if we given a job like that to each machine, then what is the finish time of this scheduling is obviously 21 seconds. After 21 seconds, all the job will be done. B will be the lastest one to finish, right? Objective, find the schedules with the minimum finish time. Can you make it better than 21 seconds? 어떻게 하면 돼? Please give me. 다시. 6, 2, 5, 14? 맞나 보다. Okay. How do you do this? You probably did it in your brain. The thing is, it's good that she find it. That's human brains can do. But in formulas, minimum finish time scheduling is something called NP-hard. NP-hard problems. NP-hard means this. Class of problems, certain set of problems for which no one has developed any polynomial time algorithms. Any polynomial time algorithms. So there is no algorithm. 폴리노미얼이 뭐야? 다차 방정식이죠? 10차든 20차 방정식이든 there is no solution for that. So it's quite difficult problem to solve. I mean, not quite. It's taking forever problems. So no algorithm whose complexity is n to the k, m to the l, known is for any NP-hard problem. So for any constant k and I, k and l, I'm sorry. Any 뭐였지? Any is number of machines. Yeah, n is number. Let's say assume that n is number of machines and m is number of jobs. I cannot find out any. I don't know what number should be in. There is no way to find out. So I don't know the time complexity boundaries for this type of problems. That is something called NP-hard problems. NP stands for non-deterministic polynomial times. 그러니까 쉽게 얘기하면 엄청 어려운 문제. 우리는 금방금방 머릿속으로 할 수 있는데 수학으로 그 어떤 공식으로 해서 미니멈 시간 나오는 스케줄링을 뽑아달라고 하면 못 뽑아. 못 뽑아. 뽑을 수는 여기 아래 보면 이제 뽑는 게 나오는데 뽑을 수는 있는데 최고를 뽑을 수는 없고 최고랑 근접한 걸 뽑을 수는 있어. That's what it means. So that's NP-hard problems. Those are the different concept later on. So NP-hard problems are solved by heuristics. This is also very difficult. Heuristics, approximation algorithm, 가정치, 가정할 수 있는 그냥 정답은 찾기가 불가능하니까 정답이랑 가장 가까울 만한 애들을 휴리스틱이라고 해요. 휴리스틱. Heuristic, which do not guarantee the optimal solution. But the solutions that I found with the heuristic algorithms, the algorithm that I can solve this scheduling algorithms will not guarantee to be the best solution. There's no guarantee. There might be better ones. So heuristic, the one we had in here is also heuristic. Heuristic too. The one we had in here is a heuristic. It can finish in 20 or 21st time. She also gave me one more heuristic solution too. Maybe her solution is the best one. Optimal one. Longest processing time, LPT rule, is the good heuristic for minimum time, minimum finish time scheduling. LPT is the minimum time scheduling. So we can use this Heap to adopt this LPT time scheduling algorithms. NP-hard는 사실 좀 어려워. 계속 나중에 그 구글에 쳐봐. 위키 같은 데 치면 NP-hard도 있고 NP-complete도 있고 조금씩 데피니션이 달라요. 그러니까 대표적인 NP-hard 문제 같은 경우에 뭐가 있냐면 나중에 다른 과목 하면 내가 얘기해 줄 수도 있는데 아침에 그 얘기 하지 않았나? 안 했나? 택배 기사분님들이 처음에 아침에 가면 뭐 하는지 알아요? 길도 찾고 물건을 빨리 가까운 데 갈 거는 앞으로 빼놓고 나중에 저녁 때 갈 거는 트럭 맨 뒤로 실어놓는단 말이야. 아니면 가는 데마다 막 트럭 뒤에 가서 뽑아가지고 하면 시간이 오래 걸리니까 그거를 머릿속으로 다 하고 이제 그거를 포함해서 내가 오늘 어떻게 돌아야 되겠다 이 길을 이렇게 다 정하시고 가시잖아. 그게 대표적인 NP-hard 프로그램이에요. 프로그램이 있어 그걸 정해주면 좋은데 프로그램이 그걸 할 수가 없어요. 즉 정확한 솔루션을 할 수가 없어요. 물론 쓰시는 프로그램도 있겠지만 회사에서 그건 휴리스틱이야. 그냥 가장 그냥 컴퓨터가 계산할 수 있는 알고리즘으로 가장 비슷하게 나올 수 있는 대표적인 문제가 그런 거예요. 되게 실질적인 문제인데 알고리즘이 없다니까 좀 황당하지. 그런 문제가 많아요. 사실. 몰라. 슈퍼컴퓨터를 몇십 년을 돌리면 나올 수도 있겠지. 잘 몰라. 어쨌든 간에 알고리즘이 NP-hard 알고리즘이니까. 슈퍼컴퓨터를 몇십 년 돌려도 안 나와요. 그런 거 그렇게 한다고 나오는 게 아니에요. Anyway, those are the very real-world examples for those scheduling algorithms. Usually, scheduling algorithms, bean packing algorithms are the typical cases for those stuff. 그러니까 택배 기사님들 머리 엄청 좋은 거야. 머릿속에 옵티멀 알고리즘이 다 있는 거야. 막상 이렇게 풀어서 쓰라 그러면 좀 힘든 거지만. I think I'm gonna stop here today. I will continue on the leftover part and plus the Huffman code too.